be recording? Oh, doesn't say so, but we are. All right, so we have one more week of numerical integration, and then we get into the final chapter, chapter 10. That's on root finding methods. Also, keep in mind, I mentioned this before recently, that you get to drop 2 assignments from a collection of homeworks and quizzes. So you might start thinking about which ones those should be, since you can see all the problems up front. Homework 7, for example, is almost entirely MATLAB. So it's kind of like homework 1 in that respect. So if you're particularly MATLAB phobic, that might be a candidate. Okay. Now, I don't have a whole ton of notes today. We'll see how long it takes to go through them. But certainly, whatever time is left for homework questions. Might not have as quite enough time on Thursday. Okay. So, first I'm going to talk about something that is useful beyond just numerical integration. It can be really used for any kind of approximation that depends on the parameter that goes to 0 to get the exact answer. So we've seen some examples of this already. Numerical differentiation, the finite difference rules depend on the spacing h using equally spaced points. And as h goes to 0, you get the exact derivative. And then with composite partial rules, I covered last time, like composite trapezoidal rule or composite Simpson's rule. In that case, you're dividing your interval AB into subintervals of some width h. And as h goes to 0, then your approximate interval converges to the exact interval. So for approximation to that form, where we have some idea of what the error looks like, we can use this technique called Richardson extrapolation to effectively cancel out the main portion of the error and get a more accurate approximation. Okay, so Richardson extrapolation is also known as extrapolation to the limit. So what I'm going to do is I'm going to illustrate extrapolation to the limit, Richardson extrapolation, using an example for computing a derivative. Now, here's one of the finite difference formulas for computing a derivative. But it's the centered difference. So I'm using this difference coefficient to approximate the derivative at x0. So what we know from Taylor expansion of f of x0 plus h and f of x0 minus h is that the exact derivative is equal to this approximation plus a term that's order h squared plus another term that's order h to the 4th and so on. And we know what these constants are. So k1 is f triple prime of x0 over 6. K2 is fifth derivative of x0 over 5 factorial. And if by Taylor expanding far enough, we can figure out what the subsequent terms are too, to whatever point we like. And in the case of a centered difference, all of these terms will be even powers of h. So we want to use the fact that we know that the leading term in the error is f triple prime of x0 over 6 times h squared to get a more accurate approximation with very little additional computation. Now, for this example, here's my function, a pretty nasty one by design. Actually, this is from, I've shown this function in class a little over a week ago. As an example of the virtues of using finite difference formulas instead of symbolic differentiation, which would be very nasty on a function like this. And okay, so x naught will be 0.25. So I can use this formula to approximate the derivative at x naught with these two h values. So 0.01, and I'll cut that in half, I get 0.005. Now, when I do that, here's the error with the larger value of h, and that's okay. And then I cut h in half, and the error is reduced by a factor of about 4, which is what you'd expect, because this is a second order accurate formula. Now, to explain how extrapolation works with these two approximations, I'm going to define d1 of h to be the approximation of derivative using whatever h. So, in other words, my approximation is now a function of h. Now, we get the exact derivative as h goes to 0. So d1 of 0 would be the exact value. So now we have the following. So my approximation with h being 0.01, but it's a larger h, would be the exact value. And then by rearranging this equation, I have approximation equals the exact minus k1h squared plus higher order terms. So I have this relationship between my approximation and my exact value. This is the leading error term. Now this is true for whatever h. So if I compute approximation at h using spacing h over 2, 0.005 in this case, I'll again have the exact value minus k1, and then I take h over 2 squared, so in other words, h squared over 4. So then what I can do is I'll go ahead and multiply the previous equation by 4. And now, if I take this equation and subtract this one, the terms corresponding to the error will cancel out. So now I have this equation that relates my two approximations to the exact value plus error best order h to the 4th instead of h squared. I've literally canceled out the leading error terms here and here. So now I just rearranged, and I'm solving for the exact value. So the exact value is going to be this simple linear combination of my two approximations. And then I have error terms left over, but those have a higher power of h than before. So now, in other words, two second order approximations were used to obtain one fourth order approximation. So very little additional computation was needed to improve the accuracy. So you're exploiting knowledge of how the error behaves to get rid of it. So that's the general idea behind extrapolation to the limit. That you figure out what linear combination of two approximations cancels out the leading error term. So it requires, this is why we go to so much trouble to figure out error formulas, because they help us obtain better approximations, as well as understand the error in the approximations that we have. So any questions about how this example played out to get a higher order approximation of a derivative? Yeah.
So I guess, okay, h is basically a very tiny increment from addition to 0, like, h divided by 2, you decrease that increment.
Yeah.
But then you multiply it by 4. Why? Why are you making that as something?
Okay, because what I have here.
Canceling the 4s in there?
Yeah, I wanted to find what linear combination of these two equations would cause these error terms to cancel.
Oh,
Yeah, and it turns out to be 4 because I'm reducing h by a factor of 2, and it's a second order accurate approximation.
so 2 squared 4.
Yes.
Yeah.
Yep. Okay, here's actually the general idea. So here I have the general form of my approximation. So approximation equals the exact plus some constant times h raised to some power p. So this is a p order accurate approximation. And then we have whatever order of magnitude for any additional error terms. So then, if I reduce h by a factor of q, which is 2 in the example, I have the exact value, and then I have same constant times h over q raised to the p power. So then, if I use the same approach algebraically that I did up here, it would amount to taking this equation, multiplying it by this factor down below, q to the p, and then subtracting this to cancel out the terms that are of order h to the p. So we can see that in the example, both q and p were equal to 2, and that led to this combination of 2 approximations here. So then I have this new approximation, and the order of accuracy is h to the r, where r is going to be greater than p. So this is a general idea behind Richardson extrapolation for any approximation that depends on some spacing h, where h going to 0 gives you the exact result. So, questions about the general extrapolation procedure? Here's another example. So still standard difference. Okay, well, it's really continue the example I had. So I used h being 0.01, and then half of that, 0.005. And I get these errors, the second order accurate. So then I take these 2 approximations. So q and p are both equal to 2. And I get a new approximation, which I'll call d2 of h. So whereas before, the error in my most accurate approximation was 7.7 times 10 to the minus 4, now I have error 3 times 10 to the minus 6, with very little additional work. And so this is now a 4th order accurate approximation. To a new page. Now, we don't have to stop here. Suppose I now compute another standard difference approximation. So before I had d1 of h over 2. That's using the original standard difference formula. Now I use this same formula, but with h over 4. And that's going to have error in 0.002. So now I could take d1 of h over 4 and d1 of h over 2, so my 2 most accurate approximations with the original formula, and extrapolate again. And now my error is going to be 2 times 10 to the minus 7, because the error is going to decrease substantially from before by a factor of roughly 16, because both of these approximations are 4th order accurate. But then, if I have 2 approximations that are 4th order accurate, I can extrapolate them to get a 6th order accurate approximation. Now, here the constants have to be different, because when I was doing these extrapolations, my parameters p and q were both equal to 2. But for this one, P is equal to 4. Q is still equal to 2. So now I'm extrapolating my two fourth-order approximations, and I get a sixth-order accurate approximation. So my error is down to 2 times 10 to the minus 10. And with very few additional floating-point operations. So 2 second-order approximations I can extrapolate to get a fourth-order one. 3 second-order approximations, I can do 2 layers of extrapolation to get 2 fourth orders, from there to get a sixth order. Yeah, so most of the work comes from computing the original approximation, d1 of h over 2, d1 of h over 4. After that, very little is needed. So it's a nice way to enhance your accuracy. You get a lot of bang for your buck that way. Okay. Just make sure to use the right constants based on your knowledge of how the error behaves. For a center difference, all the error terms have even powers of h. So that's why we jump from 2 to 4 to 6. It doesn't always work that way. It just depends on the error and whatever it is you're approximating. Your underlying method for approximating whatever it is. Yeah.
Why did you focus on center difference?
Convenience. Yeah. So if I use, like, for instance, a forward difference that is first order accurate, so that's going to have terms of all powers of h. So in that case, I'd have 2 first order approximations. I extrapolate to get second order. And then if I go through this process again to get 2 second order approximations, I extrapolate to get third order. So in that case, the power of h only bumps up by 1. So the gains are not as spectacular as they are here. So that's another reason for this one. Any questions about extrapolation? So now I'm going to show a use of Richardson extrapolation for numerical integration. And it leads to a technique that's called Romberg integration. Now, I can give a very concise description of Romberg integration. It's composite trapezoidal rule blended with Richardson extrapolation. I'll stop there, but I'm not going to. I will really show you what it is. So composite trapezoidal rule is repeated here. So my integral is equal to this approximation, composite trapezoidal rule, and then here's the error term. It's second order accurate. Now, okay, so this is something that, I don't get into in this class reluctantly, because it would be quite a pain to prepare. But I will refer you to where it's discussed in the book. It can actually be shown, and it is shown in this section of the text, 9.5, that the error in the trapezoidal rule can be described as an infinite sum of terms all involving even powers of h. So while we could stop here, we could write it in terms of something times h squared plus something times h to the fourth, and so on. And this is called the Euler-Maclaurin expansion. Now, actually, yes. Okay. So if you really want to read about this, some of you might, you get all the gory details here. What happens using some of what's called Bernoulli polynomials, you end up with okay, the Euler-Maclaurin expansion, I'll make this a little bigger. So the original integral is equal to, this is a composite trapezoidal rule approximation. And then you can expand the error in even powers of h, where these constants, the c sub r, come from Bernoulli, related to Bernoulli numbers. And then you can expand this out as far as you like, depending on how many derivatives the function f has. And then this, you can think of this as playing a role of a remainder term. Now, what matters for development of Romberg integration is that the error in the composite trapezoidal rule has this form that involves just even powers of h. So that's the part that we really need. But I'll say one more thing about the Euler-Maclaurin expansion, and that is, suppose your integrand f of x is periodic, and you are integrating over an interval that relates to a period. So for instance, maybe your integrand is 2 pi periodic, and you're integrating from 0 to 2 pi. Well, what happens is, because f is periodic, its derivatives are also periodic. So all of these terms will be 0. And in fact, almost everything goes to 0. Now, that doesn't mean that the composite trapezoidal rule is exact. But what it does mean is that when you have a periodic integrand, the composite trapezoidal rule is actually the very best integration rule. For most other integrands, general integrands, it's definitely not. But for periodic, it is, because you get this phenomenon called superconvergence, that you can show that the error goes to 0 faster than any power of h. In other words, the error is going to 0 exponentially as h goes to 0. So that's why for most applications where you need to approximate integrals, probably wouldn't bother with the composite trapezoidal rule. But if the integrand is periodic, you definitely want to. And the Euler-Maclaurin expansion is what's used to show that. So that's a fun fact about the composite trapezoidal rule. But now we're just going to use the fact that we have even powers of h. And I'll illustrate Romberg integration using an example. This is one of my favorite integrals to illustrate integration techniques. Gaussian function, e to the minus x squared, from 0 to 1. What I do is I use a composite trapezoidal rule with first just one trapezoid, so n equals 1, then n equals 2, and then with these two, I perform Richardson extrapolation. So this is the same extrapolation formula, it's just written a little differently. So you can see that the extrapolated value is equal to the more accurate one plus a correction. And we see what happens to the error. Here the error is not that small, and it's decreasing by a factor of 4 because the trapezoidal rule is second order accurate. But now the error goes down quite a bit from this simple extrapolation. And then I do composite trapezoidal rule again, this time with n equal 4, so I double the number of trapezoids. All right, the error is still not that great. But then I take this approximation and this one, so trapezoidal rule of n equals 2, n equals 4 trapezoids, and I extrapolate again, and now I get significantly more accuracy. And then I take these two extrapolated values that are fourth order accurate, and I extrapolate again, and I reduce the error even further. Although, I'm sure I don't know the typo here, 'cause that doesn't really look that great. Not sure if I have the same example here. Okay. Okay. Roughly 10 to the minus 6 versus okay, now let's do the error here. Oh. Wait. Oh, that's probably that's fine. Okay. Maybe this is the best example. But at least it shows you how the procedure works. Now, I should mention that if you look at the error to composite trapezoidal rule here, we have a second derivative evaluated at an unknown point. It can be anywhere at AB. Well, the problem is this error term is the unknown point is going to vary if you use composite trapezoidal rule, even at the same integrand, but with different values of n. So that's why you may not be entirely canceling out the leading error term. So how well Romberg integration works depends on the integrand and its derivatives. So it's easy to come up with an example where it doesn't work so well. Okay, but so the idea is you fill in the indexing here. The indices are rows and columns. You're basically filling in lower triangular part of a matrix. So all entries in the first column are composite trapezoidal rule, second order accurate. All entries in the second column are extrapolations of those that are fourth order accurate. And then anything in the third column, that's a second layer of extrapolation of a fourth order approximations to get sixth order.
Isn't some of the divided difference table?
In appearance, yes, but
Yeah,
the similarity is there.
Yeah.
Okay. Now, okay. Now this is the a version of the Romberg integration algorithm. So it fills in the Romberg table first by applying the composite trapezoidal rule, and then as composite trapezoidal rule approximations are filled in the table, then the extrapolation is performed here. It'll perform as many extrapolations as possible, given the original approximations that you have. And it keeps cutting h by a factor of 2 and continuing. So once this is done, the order of accuracy of your final approximation is 2 times capital J, where capital J is the number of composite trapezoidal rule approximations you're computing in the first place. So in this case, like the capital J is equal to 3. We use composite trapezoidal rule 3 times, like in the example, and then our final approximation or extrapolation will be 6th order accurate. And the constant here is based on the order of accuracy of whatever you're extrapolating from. As we go from one column to the next, we're getting higher order accurate approximations, so the denominator has to be adjusted for. So any questions about how Romberg unfolds? What really is loss trapezoidal rule plus extrapolation. I should mention that when I took my first numerical analysis class, let's see, 35 years ago, I had to do something like this on paper during the final exam. So, in terms of what you'll face in my final exam, you're welcome. I mean, you'll still have to do something like this, but not under 2-hour time pressure. One over problem.
We still have the set to date, just like the first exam, right?
Yes. Yeah. And, I'll have more information about that as soon as we get closer. Okay. Now, one point I want to make about this description of the algorithm is not really the most efficient. Focusing more on clarity that okay, here we're doing composite trapezoidal rule. But what happens is, as we go from one composite trapezoidal rule approximation to the next, we're always, in Romberg integration, we're always cutting h in half, in other words, doubling the number of trapezoids. So there's actually a lot of reuse of function values. And the goal of numerical integration is always to get as much accuracy as you can with as few evaluations of f as possible. You certainly don't want to repeat any. But so it turns out there is a way to update your previous composite trapezoidal rule approximation to get the next one. And I can show you that right here. So what I've done is I've rewritten composite trapezoidal rule to separate summing up f values from the odd numbered points and the even numbered points. But then what I can do with that is if I take the even numbered ones and then move those down here with f of a and f of b, then this is also a composite trapezoidal rule approximation with half as many trapezoids. And then we have these new function evaluations over here. So in other words, my trapezoidal rule approximation is equal to 1/2 my previous trapezoidal rule approximation that uses double the h, double the spacing, plus this summation where I account for any new evaluations of f. So this cuts down the total number of evaluations of f by a factor of roughly 2, just from avoiding that waste. So a practical implementation of Romberg would use this formula. What did I sign for this section? Oh, 1, 4, and 5. Okay, so I did assign this one for homework 8. So write a MATLAB function that implements the algorithm I just showed you, and then try it on these integrals. It's not going to work equally well for all 3. You just never know. Okay. So questions about extrapolation, Romberg, homework problems, any homework problems?
So exploration 9.1.5 is basically going to be modifying the original make diff rule.
Okay.
Following the instructions, find it here.
Okay, so, alright, so what you would do here is, well, since in this case, you're trying to compute the same thing, but using a totally different approach. So your code from the old make diff rule, it's not really gonna be needed here, but what no, because you're using a Lagrange polynomials. But there is some old code that you can use. It's from an earlier assignment. Make Lagrange. Because what you need to do in this function is create the Lagrange polynomials for whatever, because make diff rule, both versions take as input a set of indices, like -2 to 2, for example. So you need to create the Lagrange polynomials that interpolate at those indices, but for that you already have a function that you wrote that does that. That's make Lagrange. Oh, I think I posted it. Oh yeah, I did post it.
Make Lagrange.
Yeah, so I mean, you already wrote one from an earlier assignment, but if for whatever reason anyone hasn't done that one, you can use this. So all you have to do to get the coefficients is you call make Lagrange and you get a matrix of Lagrange polynomials. I'll go ahead and put this in the notes.
Ha. Make Lagrange.
So 9.1.5, call make Lagrange with indices that are passed to make diff rule as input. Then, once you have that, use another MATLAB function called polydir. Take derivatives of Lagrange polynomials. And now Lagrange polynomials are each row of a matrix returned by make Lagrange. So remember, make Lagrange returns a matrix. Each row of a matrix contains the coefficients of a Lagrange polynomial. And then polydir will take the derivative of one of the Lagrange polynomials, gives the coefficients of the derivative. And then use another MATLAB function, polyval, to evaluate the derivative of each Lagrange polynomial at 0. To get the coefficients of your finite difference formula, which is your output. So all of this describes what this version of make diff rule is doing. So I'll make Lagrange, get a matrix, iterate over rows of a matrix, polydir, derivative, polyval, put in 0, and then that gives you your coefficient, and you store those coefficients in a vector. The vector is called C, and then that is your output. So in fact, it's not a ton of code because there's a lot of delegation of our functions. Or any other homework questions from any assignment?
So are we done with today's lecture?
Yeah, I covered everything I needed to cover. It's a lot of time left. I was kind of surprised, like, oh my god, 22 pages of notes. I'm wondering, is that going to happen again on Thursday? I'm going to find out. right here. That's quadrant. That one's a little more substantial. Still totally doable in the time that we have. Let me guess, everybody's over and wants to go home. You'll get no argument from me.